So, hello everybody, my name's John Moffa and I'm from Castrol Lubricants in the UK, and thank you Mr. Scappaticci for inviting me to speak here today. Apologies that I have to present in English. There's a slight advantage for you guys that you get to listen to English spoken in a regional accent. I'm from the north of England, so there's an opportunity there. So firstly, we've got some good news and bad news. So firstly, in traditional style, I'll give you the bad news first. Almost everything that I'm going to say has already been covered by my distinguished colleagues. And the good news is it's almost lunchtime, so I'll go quickly and you can all leave, I hope. So I'm going to speak for about 20 minutes, maybe less if I can squeeze it in less. And it'll be in two parts. The first part will be about passenger car lubricants and about the drivers for passenger car lubricants, and the second part will be much shorter but about motorcycle lubricants, and there'll be a Q&A at the end if anybody's still here. So technology drivers, lubricant manufacturers are kind of unusual in that all of our R&D activity is sometimes or somewhat out of our control, in that the specifications that we are developing products for are set by either our customers or by legislators. So we don't have a completely free hand in what we offer to the public. And so that kind of is a different way of operating to most organizations. Right now, the people who are setting the standards by which we are developing lubricants for are thinking about, you may have guessed it, CO2 and fuel economy. So up until about 1992, passenger car manufacturers in Europe had more or less a free hand. They could make cars which produced any amount of emissions. There was no controls, there was no oversight, no regulation. And then the European Union introduced the Euro 1 emissions levels, and you can see from this chart that for both diesel and gasoline engines for passenger cars, there has been a steady reduction in the limits. And today, if you take for an example the particulate matter for diesel engines, it is reduced by over 90% from where we started in 1992. The other thing to note about this chart is that there is a convergence between the specifications for diesel engines and gasoline engines. They're coming together, and it's not impossible that maybe at a future level, maybe Euro 6 or Euro 7 for passenger cars, that we could have a combined specification covering both types of combustion, which would be potentially good news for lubricant manufacturers. So legislation is rapidly changing. Up to now, the focus has been on traditional emissions, hydrocarbons, NOx, particulate matter, and you can see from the box on the right-hand side that there's been huge reductions for all levels, not just particulate matter. But the focus now is changing. Most of the big reductions have already happened in standard emissions, and the focus now is on CO2. So CO2 is a function of burning fuel, whether it's diesel or gasoline, and if you burn a litre of fuel, you produce a fixed amount of CO2. All you can affect is how many kilometers you can drive your vehicle on that litre of fuel, whether it's diesel or gasoline. So looking at the chart on the left-hand side, you can see that there has been a steady reduction in the grams of CO2 produced for every kilometer driven in the standard European drive cycle. And the standard European drive cycle is the measure by which all car manufacturers in Europe measure the fuel efficiency and the emissions. And this is the data that is published for each car, which you as a consumer can use to judge which is the most appropriate car for you. You can see the steady reduction. There are some very aggressive targets to reach, the first one coming up next year. And the target for 2020 is so ambitious that it's likely that there may have to be some allowances made because it's a very ambitious target. So, looking at those mandatory emissions targets and just focusing on the center column that says CO2 emissions, you can see that for 2012, a European manufacturer would have a mandatory fleet average, this is measured in the standard European drive cycle, of 130 grams per kilometer. Now, because this is being introduced as a mandatory target, there is a little bit of allowances made. The first one you can see is that only 65% of the fleet needs to meet this target initially. And there are some other little pieces of negotiating room. For example, if you have vehicles which have very, very low emissions, you're allowed to count them more than one time. And if you have what's called innovative technology, which doesn't necessarily show up in the standard European drive cycle, you can make an application for an allowance for this, up to a maximum of 7 grams of CO2 per kilometre. The bottom line is that if we get to 2020 with a 95 gram per kilometre limit, the potential for a large manufacturer producing 1 million or 2 million vehicles a year, the potential for large fines would very, very quickly become obvious. So these are very serious matters, and this is why the OEMs, the manufacturers of vehicles, are looking for every way possible to reduce to increase fuel efficiency, reduce CO2, and they are looking to lubricant manufacturers to make our contribution toward that. So some technology trends in engines, and you've already heard this from the previous speakers, but right-sizing or downsizing is a very, very common trend. One way to improve fuel efficiency is to use a smaller engine. Another way to improve fuel efficiency is to make an engine with less cylinders, because less cylinders means less friction, which means more efficiency. We also have to bear in mind that by right-sizing or making small engines which are fitted with boosting particularly, turbochargers, superchargers, or combinations of both, is that when you're running the standard European drive cycle, which is the test by which we measure all of these CO2 or emissions, you can make an engine which is very fuel efficient in these low speed, low load operating conditions. But you still have the possibility to use the boost pressure to improve performance when you're driving in more real world conditions or maybe on the highway. So reduction of parasitic losses, as I said a moment ago, friction is one of the main causes or the main abilities to improve efficiency and improve fuel efficiency. So reducing parasitic losses, lubricants can play their part by having lower viscosity, and you've probably seen a move towards lower viscosity lubricants from manufacturers. Apart from the loss of cylinders, it's smaller, narrower bearings, which creates another challenge for the lubricant to maintain that oil film thickness. So advanced combustion, again, you've heard a lot about this already, but we know that advanced combustion technology is being applied now to gasoline engines in the same way that it already has to diesel engines. Most of the benefits for diesel engines has already been achieved. We know that diesel engines have moved from being not many people's choice for a car engine 10 or 15 years ago, now to being the first choice for many people because they're so efficient and so powerful. Those changes in efficiency of combustion have yet to be achieved for gasoline engines, but we're moving in the same direction. And then after treatment, you saw the fantastic improvements that have been made to conventional emissions, and the EU, who are legislating the emissions control, are not going to stop. They're going to continue to ratchet down the levels of emissions allowed, which is going to mean more after treatment, and much of that after treatment will be sensitive to contamination from lubricants or fuels. So again, we have our part to play to make that step change. So some common technology applications: gasoline direct injection, that we believe will become commonplace for gasoline engines throughout Europe, or almost required, because it gives the opportunity, particularly at these low speeds, low power modes, to run in the lean burn mode, which gives the opportunity for more fuel efficiency. Common rail in diesels was a way that diesels have ramped up their efficiency through high pressure injection, and the common rail system has now triumphed over the only other alternative that was out there, which is good news for lubricants, because the other alternative had a potential wear problem, which we're now looking beyond. Variable valve technology, it's now quite common for engines to have variable camshaft phasing, but in the future, or even now and in the future, it will become more common to have variable valve opening combined with that phasing, again to give this most efficient combustion mode. And then compound turbochargers. Standard turbochargers are okay on larger engines, but if you need performance and torque at low speed, low RPM, there has to be an additional something, whether that something is electric compressors or crank-driven compressors or a second smaller turbocharger. So this is one vision where we see engine applications could go over the next 10 or 20 years. So we're starting off in 2009, where in the past there may be 6-cylinder engines. Now we have 4-cylinder 2-litre engines replacing larger 2.5 or 3-litre 5-cylinder or 6-cylinder engines. And by 2015, those 2-litre engines will probably be replaced by 1.2-litre 3-cylinder or maybe even 1-litre 3-cylinder engines with downsizing and with boosting that, as I just described, to replace that performance. And then looking forward again, we see a reduction again to possibly 2 cylinders, 1 litre or smaller, combined with aggressive boosting and combined with some sort of hybridization to provide boost. This may not be the right way, but it's one vision that we see engine technology going in the future. So not to forget biofuels. If you remember 2 or 3 years ago, biofuels were the big news in CO2 reduction because it was renewables that were going to allow us to meet our CO2 emissions targets. Since then, the EC put in place targets for biofuel usage in Europe, and you can see that the 2010 target was 5.75% by energy content. And I think it's a fair point to say that that target has almost certainly been missed. I had a bit of a trawl around the internet to try to find some numbers, and the most common one I could find was 4.3% for last year. So, as you know, there has been some unintended consequences as a result of the EU's biofuel targets. They're outside of the EU mainly. They're in terms of what's happened to world food prices, what's happened where previous food production has been transferred into producing crops for biofuels, and even in some places deforestation to plant palm oil trees for biodiesel. So this is not good news, and I think the EC is having a little rethink about where they go with the future targets and about possibly the sourcing for the material to produce biofuel. From a lubricants point of view, bioethanol is not really a big challenge, or we don't think at the moment. Of course, when it's widely available, maybe it will be. It's been widely used in Brazil and North America for many years. It's mainly a challenge, we think, for the car manufacturers who have to make some hardware changes. Biodiesel is much more difficult for lubricants because there's issues about drain interval, there's issues about sludge, there's issues about viscosity increase, and there's issues about improperly prepared biofuel being used out there, or vegetable oil being used rather than properly refined biofuels. So car demographics, this is kind of a summary of where we're going because of the things that I've talked about earlier. If you look at the top right-hand side of the page, the chart that says average cubic capacity of new cars registered in Europe shows that up until about 2000, 2002, there was a steady increase in the size of engines being used in Europe. This kind of plateaued during the 80s, and then around the time when we entered the recession and when fuel started to increase and when CO2 became an agenda item, engine sizes started to fall rapidly. We've had a little kick up there over the last year, but nevertheless the trend is still downwards. Looking at the chart underneath that related to average power, initially, even though engines were getting smaller, average power was continuing to increase. This has challenges for lubricants again, which I'll talk about later. And on the left-hand side, you can see that demand for cars with a CO2 output of less than 120 grams per kilometre in the standard European drive cycle is going up very, very sharply. And you can see a figure of 60% increase year on year. This is a reaction to high cost of fuel. It's a reaction to the recession that we're all suffering in Europe over the last 3 years. And it's a reaction to taxation that a lot of countries have introduced increased taxation for less fuel-efficient vehicles. In the UK, for example, a vehicle that produces less than 120 grams of CO2 would cost only around 50 euros or less per year to pay for our local yearly taxation. Now, if you have, for example, a Porsche, or I don't mean to pick on Porsche particularly, but any vehicle that has very high performance and high fuel consumption, you could be paying 500 or 600 euros a year. So there's a big difference, and people are bearing this in mind now when they're choosing cars. So there's one other actor that we as lubricant manufacturers have to consider, and I know you've heard again about this, but all of the original equipment manufacturers, 25 to 30 years ago, there was very few OEMs in Europe that had their own specifications for lubricants. We relied on API, American specifications, and we relied a little bit on something that used to be called CCMC, which was very basic. Nowadays, as you can see, every OEM or every OEM grouping in Europe have their own set of specifications. They have specs for gasoline cars, specs for diesel cars with diesel particulate filters, specs for gasoline cars with turbochargers, specs for high performance cars, specs for fuel efficient cars. Now, as lubricant manufacturers, we have to offer products to meet all of these specifications, but the specifications have become very divergent, and it's impossible for us to make a small number of products to cover all of these different requirements. This is meaning extra cost for us, plus extra proliferation of different brands and products in our portfolio. And of course, making us make choices as to which ones we want to supply. So the impact on lubricants. So as I said, companies like Castrol are forced to rely on specifications from OEMs and ASEA, and lubricant suppliers must respond to every change in spec just to stay in business. That's important. We cannot stop and leave the specifications as they were, because very soon we would not be able to sell any product to franchise workshops or to any cars that are still in specification. We have to reformulate and relaunch all of our products every 3 or 4 years because of this constant change of emissions legislation leading to change of OEM car design, leading to OEM specification changes. So just to stay in business, to enable us to continue to offer lubricants that are properly specified for today's cars, we have to continue to replace our product range. So because of everything you've heard about the emissions equipment and about downsizing and all of the things that have been said earlier, and I've said myself, there are 3 main target areas that we have to think about in the future with modern lubricants. One is the protection against wear, one is against oxidation, and one is against thermal degradation. Now, because of time, I'm going to just focus on a couple of points from each of these. For wear, I think exhaust gas recirculation has had a significant impact on wear. EGR has become very, very, very commonplace as a way to control NOx emissions. And you probably saw on the table that I showed that NOx emissions is one of the latest things which is being particularly targeted by the emission specifications now that easier things have been achieved already. So EGR being dirty exhaust gas being fed back into the engine has potential impacts for wear in terms of particulate matter, in terms of dirt getting into the oil and being circulated around the engine despite the filtration system. Low viscosity, because of, as I said earlier, a way to reduce friction in an engine is to use low viscosity oil. Low viscosity oils have naturally weaker oil film, so we have to formulate around that problem to provide the protection for bearings, protection against wear, even though the viscosity looks lower. There was a common misconception amongst consumers that if you compared two oils, you had a 030 oil and a 1060, that the 1060, for example, must be better, principally because it has a higher viscosity and perceived to be thicker. That isn't true anymore. The specification of the oil has much more impact upon the wear protection of a product. And so I would urge you not to make that misunderstanding between the relationship of wear protection and viscosity. Nevertheless, low viscosity does present a challenge in terms of wear protection. Looking at oxidation, we have smaller sumps, so there's a lesser amount of oil to circulate around the engine, and the drain intervals are much, much longer. Instead of a 10 or 12 or 15,000 kilometer drain interval, we're now going 30,000 kilometers or even up to 50,000 kilometers on some diesel engines. DPF regeneration. Almost all diesel engines are now fitted with diesel particulate filters, and many OEMs have a DPF regeneration strategy which involves late fuel injection. In other words, when the exhaust valve is open, injecting some fuel into the cylinder which is meant to go into the exhaust system and regenerate the front of the particulate filter. It does have an unwanted side effect that there is potential to increase fuel dilution, which is bad for oxidation. And then thermal degradation. Turbochargers particularly, you've got higher thermal loadings per amount of oil in the engine means that there is a tendency for additive systems to potentially degrade from this continual high temperature. So we have to guard against that with the way we're designing lubricants in future. So, and lean burn, of course, means that there is potential for higher combustion temperatures. So requirements for next generation of lubricants and additives. So as I said, wear is a main thing we have to concentrate on, and at the bottom of this slide it says elemental restrictions for sulfated ash, phosphorus and sulfur. Now I know a number of my colleagues mentioned low SAPs and mid SAPs, and the fact that in Europe low SAPs and mid SAPs is becoming almost the standard for lubricant formulation style. That means that some of the common standard additives that we have always used for years have to be replaced by other products because the standard common additives are metallic elements which can contribute towards poisoning of the exhaust after treatment devices. So we're looking for replacement. So low or no phosphorus anti-wear additives, we're looking for replacements for those components. They do exist, but they're expensive, so there's a potential cost increase. More durable anti-wear performance, again, because the standard anti-wear chemistry is something which we had to reduce to make low or mid-SAPs products. And looking at oxidation degradation, TBN reduction, or total base number, in mid-SAPs and low-SAPs oils, the behavior of the base number in oils looks very, very different to what we've traditionally seen with normal full-SAPs lubricants. You tend to have quite a sharp reduction in total base number level quite early in the oil drain interval. So we're trying to maintain this for longer to improve additive retention and to improve the ability to neutralize combustion acids. So cost-effective ashless antioxidants. Oxidation increase is an important challenge, and I think cost-effective is something that we haven't yet found the solution for. Antioxidants are expensive, and there is no alternative but to continue to use more as drain intervals get longer and some sizes get smaller. Thermal degradation, cleaner burning additive, thermal stability, and improved deposit solvency. The deposits that you see within an engine as you run for a number of drain intervals mainly come from either combustion deposits or from some of the additives from the lubricant. So we want additives which are more easily cleaned up by the next fill of lubricant. So lubricants in the future, fuel efficient lubricants, everything we've all discussed today has been about CO2 and has been about fuel efficiency. So we see 0W20 and 5W20 grades becoming the norm for cars which are in warranty and which have to maintain a certain level of fuel efficiency. And high temperature, high shear values, high temperature, high shear is a measure of viscosity that is performed at high temperature with high shear stress, and it simulates very well what happens within an engine to an oil. We see that high temperature, high shear values will be so low that they will be below the standard measure at the moment that you use to establish what the grade of a product is. High temperature, high shear only goes down to 2.6 centipoise on the standard SAE J300 table, but we see as long as OEMs are compliant with this, we see high temperature, high shear going much lower than 2.6. So extended drain capability, the second big thing, we have to continue to have longer drain intervals, which gives lower cost of ownership, which is attractive to fleet managers as well as individual owners. And to do that, we have to have that TBN retention that I talked about, the ability to neutralize combustion acids, and oxidation control and added dispersancy, particularly for diesel engines. Even though we have the problem of soot in engine oil has been largely solved by the adoption of ultra-low sulfur diesel in Europe, there's still the possibility of cars as they get older becoming less, or matching the regulations less closely and putting soot into the oil. And then emission system compatibility. I said earlier that emission systems will continue to become more stringent, more demanding on lubricant performance. So low or ultra-low SAPs lubricants will become the norm for European products in the future. So in the few minutes that I've got left, I'm going to talk about motorcycles. And motorcycle products or lubricants for motorcycles are very different to those from passenger cars. And I want to spend a few minutes explaining why. So these couple of charts show the difference. If you look at the one on the left-hand side, they show sump size in different types of vehicle. And the sump is the part of the engine where the oil is stored, the oil pan. And you can see from a truck might have 20 litres or even more of lubricant within the engine. A 2-litre car engine might have 5 litres of oil. A 4-cylinder motorcycle would have 3 litres, maybe a bit more depending on the manufacturer. A 1-cylinder bike might only have 1 or 1.5 litres of lubricant. But if we look at the demands on the oil, the chart on the right shows typical oil temperature in those different vehicles. You can see typical oil temperature of maybe 80 degrees in the truck. You can see 90 degrees, maybe 95 degrees in a passenger car. And then up to 120 degrees for a water-cooled bike, or up to 150 degrees C for an air-cooled bicycle. So they're very challenging environments for lubes. There has to be ability to withstand that temperature. There has to be increased anti-wear performance in the oil. And there has to be better high-temperature deposit control. These are very different animals today than the type of oil that you put into a car engine. So there's also conflicting requirements, particularly on motorcycles rather than scooters. Motorcycles that have a wet clutch and have shared oil between the engine, transmission and clutch have to do 3 very, very different and very conflicting types of lubricant performance. For the clutch, there has to be anti-slip performance as well as anti-slip performance and also no drag performance, as well as maintaining the friction that you want to provide the drive during all operations. For engines, we have everything that we talked about for gasoline engines for cars. You have to match that for the motorcycle: deposit protection, wear protection, as well as performance, because a lot of people who buy large engine motorcycles are looking for performance. And then in the transmission, we have extreme pressure, we have high wear, we have potential pitting of parts. So if we were to design 3 different products, one for clutch, one for engine, and one for the transmission, they would look very, very different. But a motorcycle oil has to combine all of those 3 properties together. And we call this Trizone at Castrol because we produce products which have been specifically tested in all of those 3 areas. And the reason we have to produce our own testing is because within the industry there isn't a great deal that covers these areas, unlike the specifications that we talked about for passenger cars and the proliferation of OEM specifications. So motorcycle environmental factors, in the same way that up to 1992 there were very little or no specifications covering car emissions, up until about 6 or 7 years ago there were no emissions requirements for two-wheeled vehicles in Europe either. So we're now operating at Euro 3 level, or the equivalent of Euro 3 level. We're due for a change next year to Euro 4 for motorcycles. This is going to mean the adoption of catalytic converters for bikes in Europe, and some already have them. And I was reading that there was an EU Commission earlier this year was discussing the problem of emissions legislation for motorcycles. They were discussing that on the vehicles that they've tested there was very poor efficiency and life of the 3-way catalytic converters fitted to motorcycles, and they were speculating that motorcycles may have to have legislation demanding 2 catalytic converters to ensure that during the period of the life of the bike they would maintain the emissions performance. So I think that would be bad news for everybody if that's what happened. So small engine technology developments. You can see from this chart, looking at the second right-hand bar, for a Euro 3 engine at 150 cc's, the CO level is about 2 milligrams per kilometre, or 2 grams per kilometre. Now, when we go to Euro 4 next year, this is going to have to halve to about 1 gram per kilometre. Now, I know that the standard drive cycle for bikes is a little bit different to cars, but nevertheless, the target of emissions is exactly the same. So there's some substantial work to be done on motorcycles in terms of emissions control before they can be compliant with next year's target of Euro 4. This is going to mean that almost all bikes will have electronic fuel injection with 3-way catalytic converters. This is going to be required for all bikes in Europe, but there's still room, and I'm including this picture at the bottom of the steel Formix system. there's still possibilities and room for innovation within small engine design. And the steel four-mix system is a combination of taking a four-stroke engine and using some of the advantages of pre-compression of two strokes and marrying the two together to make an efficient and low emissions engine. So lubricants technology evolution for motorcycles. Excuse me. So we still see a need for low phosphorus chemistry to enhance catalyst compatibility. Honda has been driving 0.1% phosphorus limits, which was in line with API SL for lubricants, and this has now been recognized, and other Japanese OEMs have been a major driver in this reduction, which has been adopted as part of JSO T903. JSO T903 2011 is the standard motorcycle specifications. Now the interesting thing about JSO is that you combine JSO with API to say this is the specification that this motorcycle oil is approved to, but neither API or JSO involves one engine test, including a motorcycle engine. And JSO includes a clutch test which had a friction material which was not a friction material used in motorcycle clutches. This has now been corrected in JSO T903, so at least we're making some progress towards having applicable standards. So there is a possibility of an introduction in the near future of motorcycle OEM motorcycle specifications, probably from a Japanese manufacturer first, but I think that, or we think that once this begins, quite a number of other OEMs will feel compelled also to introduce their own specifications. So increased need for dedicated motorcycle formulations, I already explained why. The one little exception to that is that for scooters that have got dry clutches and automatic transmissions, there is a possibility for those type of two-wheel vehicles to use passenger car lubricants, particularly the more fuel-efficient newer type that meeting API SL or API SN. So my last slide is just a little comment that everything that I've said earlier is about specifications that are set by OEMs, and the OEMs are setting specifications and designing engines a long way before they hit the market. So lubricants co-engineering is something that Castrol is taking very seriously with our strategic OEM partners, and we are working with them to design lubricants that are co-engineered with the engine design and tested prior to the engines being released for sale, so that the engines are fit for purpose. They have all of the correct performance specifications and also the performance attributes, while still providing protection and a lower cost of ownership. So I hope that was quick enough. So if there's still any appetite, I'd be glad to take questions, but please use the mic because I have some poor hearing from too many hours spent in engine test cells, I'm afraid.
Thank you very much. Thank you very much, Dr. Moffa. I suggest to have no more than a couple of questions and combining also the questions to Engineer Caracciolo.
Just a question for all of the lubricant manufacturers. I'm wondering how much is important the reduction of viscosity to decrease the fuel consumption on a new European driving cycle, and I would like also to understand from you if the new European driving cycle is actually a good test to assess the actual fuel consumption of cars.
So two questions. My answer to the first part is that yes, low viscosity lubricants or lower viscosity lubricants are essential to meeting the CO2 reduction targets. I think this has been reflected by, if you look at all OEMs, their specifications are moving the viscosity grade that they will accept or that they mandate. They're going lower and lower and lower because it's widely accepted that In order to get the best fuel efficiency, you have to move, as I said in my presentation, to 020, 520, and lower high temperature, high shear. The second part is interesting in that there's been a huge amount of investment by everybody in the industry in measuring fuel efficiency and emissions using the existing standard European drive cycle. All the OEMs have got lots of equipment that they've invested to measure this, and everything is designed and targeted to match the requirements of that spec. Now, I think the EU is recognizing that the speed and the vehicle speed and load and time and duration of the current drive cycle maybe is lagged a little bit behind where we are today with vehicles. It's very low speed, very low load. But because we have all of the targets in place that are all built around the current drive cycle, it would be very difficult to change it. But I'm sure that there's a lot of discussion going on to think at least about how we address this issue. I don't know if any colleagues want to say anything on that.
Thank you very much.
Yes, it's an opinion, of course. Yeah.
You have perfectly explained what's the shift towards lower viscosity grades are happening on lubricants now. I just would like to ask you, what's your opinion about the impact that can have on this kind of trend, the phenomenon of oil dilution, the contamination that's due to biofuel? Do you think really that it can affect this trend in the future, or this future to lower and lower viscosity grades will stay like this?
Well, I don't think fuel dilution correlates with viscosity grade in any way, but it may be a more serious problem, obviously, with a lower viscosity lubricant. And what you said kind of leads me to make a sort of proviso that the low viscosity trend will be lower for gasoline engines than for diesel engines because of the increased loadings and the increased wear. But I don't feel that there's a relationship between, in gasoline engines at least, there's a relationship between fuel dilution and a restriction of that on viscosity. As long as your engine is, of course, operating properly.
So in this moment, the manufacturers, especially for heavy duty, they're just suggesting to reduce the oil drain intervals.
Yeah, and you're right about heavy duty. I didn't mention heavy duty at all in my presentation, but the same trend that we're seeing for passenger cars, to a lesser extent for motorcycles, is also applying for heavy duty. 1540 oils are no more on new trucks. It's now moving towards 530, and I think Castrol, as everybody probably knows, we have marketed for some time a 030 product, but I have to admit that it's had some it's not been widely adopted. A lot of people are concerned about the possibility of a 030 product in a heavy-duty engine, even though we've got plenty of data to show that the performance is absolutely fine.